the strong acid with a pH of 2. So that's solution A. Nitric acid and hydrochloric acid are strong acids. Give the name of one other strong acid. There are a number of options, but the one you should know is sulfuric acid. There are 3 acids that you need to be aware of for this syllabus: nitric, hydrochloric, and sulfuric. Write the formula of the ion produced by all acids in aqueous solutions. So it's the equivalent of this ion here, and with it being an acid, we're looking for a proton or H+. And again, as it's dissolved in water, then it will be a good idea to put the AQ for aqueous. Ammonium hydroxide solution, so the hydroxide tells us it's an alkali, reacts with nitric acid according to the following equation. So ammonium hydroxide reacts with nitric acid to make ammonium nitrate and water. So this is an acid and alkali reaction, so we should be thinking that we're making a salt and water if it's an acid alkali, and indeed there's our salt and there's our water. Give the general name of the type of reaction taking place. Well, this is an acid reacting with an alkali, so we'd call that a neutralization reaction. Okay, now it says complete the ionic equation for this type of reaction. Okay, so we've got a hydroxide or an alkali, and we've got an acid. Previously in the question, we've established that the ion formed by alkalis is the OH- ion, and the ion formed by acids is the H+ ion. Okay, so the question asks us for an ionic equation, so it would be rude not to put in OH- and H+. Now if we check here, we've got 1 oxygen on this side of the arrow and 1 on that side. We've got 2 hydrogens on the left-hand side of the arrow and 2 on the right-hand side. These two cancel each other out electronically, and consequently we've got no charge on this side. Okay, so that's the finished question there. So number 2, magnesium nitrate can be made by adding excess magnesium oxide to nitric acid. State why excess magnesium oxide is added. Well, this is to ensure full neutralization of the acid. Because we can remove the remaining solid, whereas we couldn't remove an unreacted acid, this is the best way round. The following apparatus could be added to remove excess magnesium oxide from the solution. Complete the labelling of the diagram. So it's a little bit unclear, but this is a filter funnel, and the material left in the filter paper is the unreacted magnesium oxide. Which can then be discarded, leaving this solution of magnesium nitrate at the bottom. State how you can obtain magnesium nitrate crystals from a solution. Okay, a key word here would be evaporation. Basically, we can either heat it strongly to force the water off, or better still, leave it to evaporate naturally over a long period of time. That way we get bigger bigger crystals. This is sometimes called crystallization. So those two would both have been equally valid. Okay, moving on. Okay, so this question included or involved rather a little bit of interpretation, but also some actual knowledge. So we've got here a picture of a nappy, a gum shield, a baby bath thermometer, which tells us when cold it's yellow and in hot it's orange, and then some sunglasses. So when it's overcast, you can see through the glasses, whereas it's sunny, you can't see through the glasses. So use the above information to complete the table. So it changes colour when changing temperature. So that would be the use would be the baby bath thermometer. And then the type of smart material is a material that changes colour due to temperature. Okay, so temperature would be the thermo, and the colour change is chromic. That's a thermochromic pigment. Is used in the making of the ducks. It regains its original shape on heating. That'll be a gum shield, because if you have if you're biting down hard on your gum shield during the game, then it will deform. Or if you have a collision with somebody, it will deform. But then when you want to use it again for your next game, you need to be back in the original shape. So for that, we'd use a shape memory polymer. There is such a thing as shape memory alloys. However, you don't really want to put a chunk of metal in your mouth when you're playing a contact sport. Okay, so shape memory polymer. It changes colour with changing light intensity, so that will go through the sunglasses. And the material used in these sorts of sunglasses is photochromic. So photo is to do with light or colour. Well, no, sorry, light. And then the chromic is the changing colour. So they change colour depending upon the light. Okay. Now you need to get both sections of that to get the mark. Okay. So unfortunately, you might have got that bit right, but if you didn't get that bit right, you don't get the mark, and this is often the way with an exam paper. Right, number 4. Heled was asked to make some silver bromide, AgBr. She formed a white precipitate of silver bromide by mixing solutions of sodium bromide and silver nitrate. So we've got the sodium bromide solution going into the silver nitrate, and that creates a precipitate of silver bromide. Okay, so write a simple equation for the reaction. Okay, so we're told that she uses the sodium bromide. So sodium is Na and bromide is Br. Okay, now as it's a solution, we could put Aq there. Also, to confirm the formula of this, it would be useful to use the table of ions. Unfortunately, that wasn't available to you in here, but as it happens, that is the correct formula. Okay, and it's actually given to you in the question there. Okay, so that's handy. And that is reacted with silver nitrate, and silver nitrate is given to us in the question. That's AgNO3. And again, as it's a solution, it might be an idea to put Aq. A reaction happens, okay, and we know that we're going to get AgBr, okay, because that's what we're after, the silver bromide. Now, what we know about silver bromide is that it's a precipitate. So if something is a precipitate, then it's not a solution, it's a solid, okay, because we can see it in solution. And the remaining product, okay, is whatever's left over. Okay, so we can assume from the formula that this is going to be a balanced equation. So the stuff that's left over is sodium nitrate, and that would be a solution. Okay, so it's, the state symbols weren't requested or required, but it's nice if you can put them in just to confirm your understanding. Okay, give the name of the process that Heled should use to separate the precipitate of silver bromide from the reaction mixture. Okay, so if we just whip back a couple of questions, you can see this this experiment here with the filtration. So that's a helpful question there, because we would use filtration, because we need to remove the insoluble precipitate of silver bromide from the solution. Okay. Calculate the relative mass, formula mass of silver nitrate, AgNO3. So we know, and in the question we're given the relative masses of the individual elements. So AgNO3. So Ag weighs 108, N weighs 14, and 3 times 16 is 48. So the MR of AgNO3 equals 108 plus 14 plus 48. Okay, these 3 values here. And if we confirm that on the calculator, okay, we've got our 108 plus 14 plus 48 gives us 170. Okay. And part C says the relative formula mass of silver bromide is 188. Okay, so that's a different compound to previously. Calculate the percentage by mass of silver in silver bromide. Give your answer to 1 decimal place. So silver atom weighs 108. Okay, there is 1 silver atom in silver bromide. We can just double check that up here. So AgBr. So the total mass of this stuff is 188, as given in the question. We want to know what percentage of that is silver. So that would be 108, which is the mass of silver, divided by 188 times 100%. Okay, so if we put that into the calculator, so we've got 108 divided by 188 equals that, and then times 100. And then remember that it says to 1 decimal place, so that would be 57.4. 57.4%. Okay. Okay, then, the next part of this question. A piece of work in Helen's exercise book showed the results of 2 tests that she carried out to identify some ions in the chemicals she had investigated. Use your knowledge of chemical testing to complete the table below. Okay, so we're going to add, so for the carbonate ion, we could react the compound we suspect to contain carbonate with an acid, in this case nitric acid. And when you do that, it's the reaction of an acid and a carbonate, and the products for that reaction are salt, water, and carbon dioxide. And so carbon dioxide is a gas, so we'd expect to see bubbles formed as carbon dioxide gas is produced. Okay, so it doesn't say explicitly, but the name would be desirable, although the formula would also get you the answer. Now for the sulfate ion, it's a very specific test. We need to add barium chloride solution. When you add barium chloride solution, the barium reacts with the sulfate ion to make barium sulfate. See, these are both named tests in your specification, so you do need to know them. So barium sulfate is a white precipitate, so we can see that that's the indicator of the sulfate ion. Okay, write the ionic equation for the reaction that took place in test 2. So the product is barium sulfate. Okay, so barium is Ba and sulfate is SO4, and this is a solid. And just to confirm that barium is a 2+ ion, sulfate is a 2- ion, so that is the correct formula. And consequently, we'd need a Ba 2+ and an SO4 2-. Okay, so the absence of an ion table in your paper, that would have been more difficult. Okay. Okay, number 5. The diagram shows 3 reactions used to prepare soluble salts. So in the center of this reaction scheme diagram, we've got dilute HCl, which hopefully you should recognize as hydrochloric acid. So this question's about the reactions of acids. So we're thinking acid plus metal is salt and hydrogen, acid plus water is acid plus alkali rather is salt and water, and then acid plus a carbonate is salt, water, and carbon dioxide. So if you react HCl with zinc, then we get zinc chloride solution because it's soluble, and hydrogen gas because it's a metal. The hydrogen gas is a confirmation that we're reacting a metal here. Reaction 2 with compound A. So the word compound implies that it's going to be more than a metal, so it could be hydroxide, an oxide, or a carbonate. We get magnesium chloride solution. Now that word there, solution, implies water. Okay, so we're just getting some additional water maybe. And then finally, we've got a copper carbonate. Okay, so we've got acid reaction with copper carbonate, so we know we're going to get a carbonate, we're going to get water, and we're going to get a carbon dioxide, okay, which is that gas there. Sorry, we're not going to get a carbonate, we're going to get a salt, and we're going to get water, and we're going to get carbon dioxide. So with that in mind, let's have a look at the questions. Name compound A. So compound A produces magnesium chloride solution and water. So the ideal answer to that would be magnesium hydroxide. or actually magnesium oxide. Okay, so magnesium oxide would work, but so would magnesium hydroxide. So either of those two would give that result. Then write a balanced symbol equation for reaction 2. Okay, so this is reaction 2 here. So at this point, if we choose one, let's choose magnesium oxide. So magnesium oxide is MgO, and that's a solid. And that's going to react with HCl, which is an aqueous solution because it's an acid. And that's going to make magnesium chloride. Now, magnesium chloride is MgCl2, because if you had access to an ion table, you would know that magnesium is a 2+, chloride is a 1-, so you need two of these, and we're going to get water, H2O, which is liquid. And if we look at the balancing situation, we've got one magnesium, we've got one oxygen, we've got one hydrogen, but we've got two here. So in order to solve that, we need to put a 2 in front of the HCl. And in doing that, we automatically solve the next problem, which was the chlorines. We've got 2 chlorines here and 2 chlorines here. Okay, so that's the balanced equation. Okay, give the names of the blue solution B and gas C formed in reaction 3. So we've talked about this already. So if you've got hydrochloric acid reacting with copper carbonate, we need to recognize that hydrochloric acid forms chlorides, or metal chlorides, and the metal here is copper. Okay, so the salt is going to be copper chloride, so that's the blue solution. So copper chloride, and then the gas is carbon dioxide. Okay, so that's always made when you react a carbonate with an acid. Carbon dioxide. Okay, reaction 1 was repeated using magnesium instead of zinc. Explain the difference, if any, that you would expect to see. Okay, so you would expect to see more fizzing, greater heat given off, and that's because magnesium is more reactive than zinc. Okay, and then give what then one metal that does not react with dilute acids. You have a few options here. Gold would work, silver would also be correct, and even copper. Okay, those three would be acceptable. There are others, but these are the most popular, if you like, and most obvious ones. Right, the salt formed when zinc reacts with nitric acid is zinc nitrate. Complete the symbol equation for the reaction by giving the formula for nitric acid and zinc nitrate and balancing the overall equation. Okay, so zinc plus a number of nitric acids. So nitric acid is HNO3, and it's aqueous. And then we've got zinc nitrate. Now zinc nitrate is Zn, open a bracket, NO3, close the bracket twice. Okay, and because of this 2 here, then that tells us that we need a 2 here. So that ensures that we've got the 2 hydrogen atoms to make the hydrogen molecule, and then we've got 2 nitrates altogether to react with the zinc to make the zinc nitrate. The reason that this formula is like this is because if we look at the table of ions, zinc is a 2+ ion, nitrate is a 1- ion, so you need 2 of these to cancel out or balance on one of those. Okay, number 6. Automotive and aeronautic spark plugs contain electrodes which connect the ignition to the engine. As the plug detects electricity, a spark is then created, which starts the combustion process and starts the engine. High quality spark plugs are tipped with platinum. Platinum is a typical metal. Describe the structure and bonding in platinum. So this can be done with a diagram. Okay, so a metallic structure consists of a regular lattice of cations or positive ions. That would be 1 mark. pointing this out, this regular arrangement. And then the regular arrangement of cations is surrounded by a sea of electrons which have come originally from these atoms. Okay, so this sea of electrons is around and about the whole of the structure. Okay, so if we label these items, so a regular lattice of cations, and these dots represent a sea of electrons, and that's for 2 marks. The third mark is the strong electrostatic force. So these two components are held together by a strong electrostatic force. In other words, opposites attract because the electrons are all negative. Okay, so the whole thing is held together by this electrostatic force. Okay, explain how the bonding present makes platinum a good conductor of electricity. Okay, so the sea of electrons, and we could even put in the word delocalized electrons. Can carry charge. They are negative, and they can carry charge through the material, or carry current through the material, through the lattice. So the flow of electricity is simply these electrons moving through the material due to an external force. Okay, number 7, hydrochloric acid, HCl, reacts with sodium hydroxide solution to form sodium chloride and water only. Write a symbol equation for this reaction. Okay, so HCl you're given in the question. You could put in the AQ just to be clear. Sodium hydroxide, we've come across previously, is NaOH. HO will do, however, that's the conventional way of writing hydroxide with the O first and the H second. And then it tells us we're going to get sodium chloride. So sodium chloride is NaCl, and water, which we know to be H2O. So if we have a look at this, we'll discover that we don't need to do anything to balance this because it's already balanced, but we could put in the AQ here, and we could put in the L there. So there's one hydrogen there, but there's another one here, and there's an oxygen, so that makes the H2O. There's a chlorine here and a sodium there, which are matched in the sodium chloride. Okay, a group of students uses a sodium hydroxide solution of concentration 0.25 moles per decimeter cubed to determine the concentration of a sample of dilute hydrochloric acid. They measured exactly 25 centimeters cubed of sodium hydroxide solution and titrated it against hydrochloric acid using the following apparatus. Okay, so in here we're going to have 25 ml of sodium hydroxide, and in here we're going to use this to measure a mystery volume of HCl, and by doing a bit of maths we can work out the concentration of the acid. Okay, so the name of the piece of apparatus is labeled X. Okay, so this is X and this is a pipette. We didn't use the pipette itself when we did this experiment. We used a measuring cylinder, but a pipette is a measuring device with a line that accurately depicts the volume written on the little label there, which for this one is 25. Okay, so at 20 degrees Celsius, this measuring apparatus will deliver 25 centimeters cubed of liquid if you fill it up to that line there. Explain why a burette is used to add hydrochloric acid. Okay, and this is because it is accurate, which means when it says 25 centimeters cubed on the scale, it means 25 centimeters cubed, but also it's precise. Okay, so it's accurate and precise. What that means is the graduations, the steps on the burette are very small, so we can be very precise with our volumes. Okay, you should be able to measure to 0.05 centimeters cubed with a pipette, a burette rather, with a burette. Okay. Okay, explain the purpose of the indicator. And the purpose is to show the end point of the titration. And in this particular instance, that means neutralization. So you know how you added the right amount of the solution in the burette when the indicator indicates that the solution is neutral. Okay, and we call that the end point in a titration experiment. Okay, number 4, use the results below to calculate the mean volume of hydrochloric acid needed to completely react with 25 centimeters cubed of sodium hydroxide solution. Now, the point of titration is to get precise and accurate results. In other words, similar results, but repeated to ensure that you've got the right value. If we look at these results here, we've got a 12.5, a 13.7, a 12.4, and a 12.6. So this result here, number 2, is significantly greater than the rest. So when we're calculating a mean, we wouldn't include it. Okay, so to calculate the mean, we need to do 12.5 plus 12.4 plus 12.6, and then we need to divide those by 3. But you might notice that actually these 3 numbers are 0.1 apart from each other, so it tells us that the mean is actually 12.5. Okay, so 12.5 is the mean volume of acid required. And then the final question says, use the results of the titrations. Okay, so that's the 12.5, and the concentration of dilute hydrochloric acid relative to the 0.25 mole per decimeter cube of sodium hydroxide. So we're looking to find the concentration of the hydrochloric acid. Okay, so we used 25 centimeters cubed of 0.25 moles per decimeter cubed sodium hydroxide, and that was neutralized by 12.5 centimeters cubed of, we don't know what that value is at the moment. Let's just put these NaOH. We want to know the concentration of the hydrochloric acid. Okay, so basically that's half that value there. So this concentration here must be twice. Okay, so 0.5 would be the concentration. So you need half the volume of the acid to neutralize the sodium hydroxide. As we saw earlier on, this is a 1-to-1 reaction. Okay, so we need the same amount of sodium hydroxide as we've got hydrochloric acid. So we need to double the concentration. Okay, so the concentration is double. Right, final question. Self-cleaning glass windows use a nano-sized titanium dioxide. A 15 nanometer layer of nano-sized titanium dioxide becomes transparent when it's applied to glass. Self-cleaning glass reduces the need for detergents. The flow chart shows how self-cleaning glass works. It tells us that dirt forms on the nano-sized titanium dioxide coating, which is the thin white layer. Sun shines on the window. The UV rays trigger a chemical reaction in the coating, which breaks down the dirt. So rather than big lumps of dirt, we've got the dirt more spread out. And then water hits the glass. It spreads evenly over the surface instead of forming droplets. So runs off and takes the dirt with it. Okay, so you wouldn't get the droplets of water on the surface. The water just runs straight off. So state the meaning of nano size. That's a very specific answer we're looking for there. Nano size is between 1 and 100 nanometers in size. That's what the phrase refers to. Okay, state why nano-sized titanium dioxide is suitable for self-cleaning windows. Well, if we look in the description, it tells us that it becomes transparent. Okay, so it's transparent, which is handy if you're a window at nano size. And also, you could mention the fact that this chemical reaction occurs, which turns the dirt into it breaks the dirt down. Rather, it breaks the dirt down. Okay, but either of those two would do. And then C, titanium dioxide has been used in sun creams for decades. Sun creams available today use nano-sized titanium dioxide particles. Some people believe using sun creams containing nano-sized scale particles is unsafe, give the advantage of using nanoscale titanium dioxide particles rather than larger titanium dioxide particles to make sunscreens. Now, where it uses the word larger there, we might in other papers, other exam papers rather, use the word bulk. Bulk means bigger than nano size, basically. Okay, so the advantage is that nano size sunscreen is transparent. Okay, so the nano size particles are transparent. They're so small that they're transparent, whereas the normal sized or the bulk sized particles, they form that white cream that people put on their faces, etc., and look a bit foolish because it doesn't rub in very easily. Okay, so that's the advantage. The next question asks about the disadvantage. So explain why some people are concerned about the use of nanoscale titanium dioxide particles in sunscreens. We've got 2 marks here, so we need to make 2 points. The first one is that nanoparticles can pass into the blood and we don't know the effects of this. Okay, so we don't know the long-term effects. Okay, so it might be that they're completely harmless, or it may be that the titanium dioxide has some impact on people's health further down the road. Okay, now this one says approximately how many times bigger are common titanium dioxide particles, which are 4 times 10 to the minus 7 meters across, than nanoscale titanium dioxide particles at 3.3 times 10 to the minus 10. So in order to calculate this, we need to do a bit of a division. So 4 times 10 to the minus 7 meters divided by 3.3 times 10 to the minus 10. So these particles are the bulk ones, the big ones, and these are the nanoparticles. So if we put that into our calculator, so let's get rid of that previous calculation. So we've got 4 times 10 to the power minus 7 divided by 3.3 times 10 to the power minus 10. And that gives us 1,212. Okay, so that's 1,212, which is equal to 1.2 times 10 to the minus 3, which is also equivalent to, it says approximately here, so maybe we could go for 1,000, but let's put in the 1.2 times 10 to the minus 3. Not minus 3, sorry, plus 3, or just 3. And then finally, silver nanoscale particles are used in socks and plasters. So this is silver rather than titanium dioxide. Explain why nanoscale silver is used in these products, and it's because it's antibacterial, basically it kills bacteria and indeed other microorganisms, okay, and also kills other microorganisms which cause the smell in socks, but also cause infection in cuts. So therefore, your plaster would help to reduce that infection. Microbes. Okay, that's that then.